Somebody remind me what S is, for example. Of what? Sample. I love it. What is, this is going to be weird. What is its job? What is its job? True. So if we take a sample, we're curious about the average age of gross amount. We take a sample, we get the sample mean. What is the sample mean's job in that situation? This is such a weird question. I know. I'm telling you right now, it's a weird question. We're curious about the actual average age of gross. I'm sorry, Chuck. We're curious about the actual average age of gross amount. We go take a sample, we get a sample mean. What is that sample mean's job? Yes, we're hoping if we pick a nice, good, random sample, large enough, we're hoping that X bar approximates the real mean, correct? If we knew the real average age, would we ever use X bar? No, okay. So, take a sample and we calculate S. What's S's job?
Give us a feel of the real.
Say again?
Give us a feel of the real.
Yes, to estimate the actual population standard deviation. So if I know the actual population standard deviation, I'm not going to use it. I'm not going to use S. I'm going to use sigma. Now, remind me, your question exactly was?
Oh,
that's right. Sorry, Sean. It's like, oh man, I've always been absent-minded. As you get older, come to find out, that gets worse. Okay, so if we don't know blank, then we use blank. So if we don't know sigma, we use S. If we don't know mu, we use X bar, right? If we don't know P, what's P mean? Versus P hat.
P is the actual percentage.
Percentage of the population, P hat,
Percentage.
percentage of the sample. I love it, right? Everybody with me so far? This has come up a few times, but I've never said it this directly. In a hypothesis test, one of the main things to understand about a hypothesis test, let's say that our null hypothesis P is 0.6. We're going to assume it actually is 0.6. So this is the equivalent of somebody making a claim, and so somebody says, "Oh, you can't bench lift over 200, right? Something stupid," and then you bench lift 210. Like, oh, okay, assuming you're right. Look what I just did, right? That's basically a hypothesis test. Assuming you're right, look what we just did, right? So somebody says it's 60%, and we get a p hat of 90%. That most likely will be good evidence that it's not 60%. So assuming this is true. So when you go to check, is it normal? You don't do NP hat. No. Why would you use a p hat? Because you know what p is. Maybe. So a few of you guys, when you check to see if it was normal enough, and this is number 2?
Yeah, 2B.
Yeah, number 2. On number 2, when you go to check if it's normal enough, first off, you have to use NP-NQ. Secondly, you don't do NP hat, NQ hat. You do NP, NQ. Okay, maybe. I know this is weird, but that's what, again, I love that idea, because you've heard this. Assuming you're right, look at that shit, right? Somebody says, hey, no, nobody ever got a empty M&M bag out of it. Assuming you're right, look what I just did. It's empty, right? Or whatever. It's horrible. I got bench lifting and M&Ms as examples, so I'm sorry. Anything else from the test? Yes?
7E.
Seven was the correlation. 7 was the phantom 6. Yes. Okay. All right. So we know that if the temperature goes up, you're not going to sell a lot of hot cocos, or if the temperature goes down, you're not going to sell a lot of ice creams. That kind of makes intuitive sense. If we just do a correlation analysis and bring nothing else in, all we know is that there's a snapshot correlation. So for example, how do I say this? I could show a correlation. I bet you that there's a correlation between the first letter of your last name and the grade made by students. If I take a large enough sample, I can show a correlation. You guys semi with me? Everybody understand what I'm saying? Does that mean that if you go change your last name, let's say that people that have a W for the last name get higher grades than somebody's got a B as a last name, and let's say your name is Princeton Bridgerton, right? So you say, okay, I'll just change my last name to Princeton, whatchamacallit, W first letter. That correlation analysis tells me my grade's gonna go up. Right. I understand that whole thing I just said is kind of weird, but do you understand right there what the problem is? It's a snapshot. It goes, oh, it seems that there's a correlation between the letter of the first letter of the last name and grade. That says nothing about what if I changed this, right? So if I take, so what is this? Let me go even deeper. What does this problem leave out? What else could affect? So some of you guys had hot cocos, right? And some of you guys had ice cream cones. Yes, ice creams. Not there, but okay. What if I could magically? No, let me not go there. I'm sorry. What else does it leave out? What else could affect the number of hot cocos besides temperature of the day? What else could affect the number of hot cocos, the number of ice creams that I sell?
Economic state.
Sure, economic state. Sure. Like maybe on payday, the sales of everything goes up. So that's in there. Are you with me? There's another variable that's in there that did not take into account, correct? What else could affect? How about days that people are off? They're actually able to go get ice creams and hot dogs and so forth. Yes? Maybe? No? I mean, there's all kinds of things that could possibly dictate. Maybe there's a new commercial that came out that everybody's like, okay, ice cream. I forgot that existed. I'm gonna go get some ice cream. Have you ever done that? Forgot something existed and like, oh yeah, that exists. Oh, okay. You guys semi with me? There are other variables besides just this. So the analysis by itself says nothing about if I change this, will this change also? It says nothing about that. It could lead to us creating a study that would do that, right? So, for example, real quick, if I go SATs, are you guys still taking SATs? Anybody taking the SAT? Is that still a thing?
Yeah, I took it.
You took it? Okay. Yeah, I remember taking that crazy. Okay. Let's say that we notice that people who have taken a certain prep course get higher scores on the SAT. We just noticed that. Is that evidence that if you went and took that course, you would get a higher test score? No. By itself? No. How would I test that? I could take a group of people, have them take the SAT, then have them go take the test course, and then have them take the SAT again. That would be a study that would see the effects of this one thing on this other thing. Are you guys with me? It's a very bare bones study, but that's basically, in fact, when you do a drug study, you have to kind of have a control group and so forth, right? And that's what's missing here. So this can only give an idea that there seems to be a relationship. We don't know which way it goes. We don't know if it's caused by a third thing, right? Okay. Because again, how many variables does a correlation analyze at once? 2. And if they're both affected by some third variable, I could see a correlation and think something wrong. I could make wrong assumptions, yes? Maybe. So a correlation study is like a first level statistical analysis, just to see if there even makes sense to go deeper. Does it even look that there's a relationship that I want to try to create an experiment to see if there's a causal relationship? That would be a next level thing. You guys kind of with me? I know. Some are so damn fast that we have no time to really get into the stuff. Okay. That's a beautiful question. I forgot to ask the question already. Did you ask that? Who asked that question? You did. Okay. Is that all right, everybody? Okay. What's up?
I wanted to know for 2B, do we use these scores or nothing and why?
Yes. So we just had a discussion. That's the one, n greater than 30 is not good enough because that test was about percentages. So what do you have to check when it's percentages? NP and NQ. And the P, we're assuming it's the P from the claim. So you don't use P hat, you use the P from the claim. Okay. However you feel about this class, it's almost over. It's almost over. Oh man, I can see some of your faces. Oh, what have I done? Okay, we're almost there. Anything else on the test or on the grades? Did everybody get their stuff back? Sally? I'm sorry. So any homework that has no marks on it is assumed good.
Okay.
Yep. All right. It's about half of what I started with. Well, there were a few people that said they weren't going to be here, so that works out. All right. Yes.
We were supposed to pick up the review thing yesterday, right?
Oh yeah.
I didn't sorry.
It's up on Canvas too. Does anybody else? That was my fault I should have passed it out before the test started. Anybody else see the practice final? Everybody else is good. Okay. I'm gonna give the answer key for that tomorrow. Because. That's right. That's that. All right, guys. If there's no further questions, we have one chapter left. What I'm gonna do. Let me remind myself what I'm gonna do. So the one thing is the one chapter we skipped. Chapter 10 was extra credit, so we didn't really skip it. We skipped chapter 11, and I explained at the time why I did it. So you know what you're going to get today. We've gone through the z-score chart, then you got the t-score chart. So now today you're going to get the last chart. The final chart. So, I think what I want to do, let me double check something. I know for sure, here we go. Yeah, okay. So let's do this right off the bat. Let's do this, all displays. Let me think about that. Yeah, I think I want to do that. Yeah, I definitely do want to do that because I think this is called pedagogy on the fly. Let me see. Yeah. Good. You definitely don't want to do that. Okay. I'm going to immediately make our future life better by saying section 11.6 is extra credit. So we're just going to do section 11.1, section 11.2. Is everybody with me? And you're all like, you can make it all extra credit if you want to, Jeff. We'd be okay with that. Oh, you guys are awesome, but no. Okay. So, let me start off with some what should be really obvious stuff. Let's talk about stuff we've done already and build it up to what the hell this section's all about, this chapter. Oh crap, okay. How many z-score formulas do we know? Can somebody give me one?
X bar,
Keep going.
plus or minus.
No, that's a confidence interval. I want a z-score formula.
That minus mean.
So what's the most basic one? X minus mean divided by
Square root of that, or just that.
sigma. Then we got the next level, which is x bar minus the mean divided by sigma x bar, right? So that's the one we use. That's like our z star. Is that the only z-score formulas we know? Isn't there another one we just learned for hypothesis test? Another z star. This is for means.
It's yeah, then it's over like square root of q over square root of
All three. Those are three. Now I would argue they're the same concept, but there definitely are three different formulas. Do they talk about three different pictures? What do these all kind of fall into? What kind of distribution do they?
normal.
Normal. For the most, of course, you have to show this normal, blah, blah, blah. But for the problems that we're able to do, they all fall into a normal distribution. Correct? You guys with me? So the z-scores are sort of what builds this picture. So how many z-scores have how many data points have a z-score of 0? The most, right? If I'm taking repeated samples of a population, the most common thing I should get is the actual mean. So that's why that's got the highest bar. That also is another, we talked about this when we talked about central limit theorem, when we went to alternate universe Florida. If I take a sample of 30, what's the most likely thing? A mixture. It should be the actual mean. That should be the most likely thing. That's one reason why it makes sense it starts to become more normal, because the highest peak is in the middle. Okay. Now, trying to figure out the order to do this in. What tells me, yeah, good, okay. What tells me kind of the shape of this thing? Like, what tells me if it's skinny or fat, or like really skinny,
The spread.
which is the standard deviation. Okay, cool. So the picture fundamentally looks the same, it just has these parameters. The mean kind of moves it around, it tells what the center is, and the standard deviation kind of makes it skinnier or fatter, right? Okay, everybody with me? All right, I love it. So means follow this curve, percentages follow this curve, and the standard deviation is what tells me. So for this picture, how many standard deviations are there? It's a weird question. Like, there's one. There can't be more than one, because then it would be skinny and fat at the same time. You guys kind of with me? Okay, maybe. So, this, just like when we went to alternate universe Florida and we took a bunch of these, and then we graphed it, didn't that become a normal curve, right? When we got a sample size bigger than 30. What if I took samples bigger than 30, but instead of getting the mean, doesn't even have to be bigger than 30, let me be careful. What if I took samples, and instead of calculating the sample means, I calculate the sample standard deviations instead? Won't I then get a bunch of standard deviations?
Yes.
Because if I had Florida, how many groups of size 100 could I pick from Florida? A lot, right? I don't want to think about it. I don't want to go back to Florida. I did my time in Florida. Right? So then every time I take a sample, I can get an S. And then I go take another sample, I get another S, I get another S, I get another S, I keep going, go crazy. What the shit would that look like if I graphed all of those?
Also normal.
Well, no, in an extreme case, if I take a large enough sample.
Be like a bunch of waves.
So here's what happens. So normal curves result from plotting means, for example, or percentages if the conditions are met. Like if n is greater than 30, or if np and q is bigger than or equal to 5, it'll become a normal curve when I plot those things. What happens with standard deviations? Yeah. So let me do this. All right, I've decided what order to do this in. Z-score is the variable we use to describe standardizing a mean, standardizing percentages, correct? Here we go, you ready? when I have a bunch of standard deviations and I standardize them, it's not z, it's chi-squared.
It's not an X.
It's a symbol, it's not an x, it's a Greek letter chi. Right? Doesn't have anything to do with Dragon Ball Z. And the square is a part of the symbol. Do not square root. You with me? The square is a part of the symbol. If you square root it, it's like, I don't know what I am. Okay, so don't do that. So here's what's interesting. So just like, remember I showed you the formula for the normal curve? Do you guys remember that? Maybe I should do that again. Yeah, let's revisit that. It's a good idea. This is what happens when Jeff spends all his time grading shit and none of it getting ready. So I'm sorry. Hold on. I want to show you that formula one more time. This is going to relate immediately to what we're doing. Where would you be? I could try to write it down, but I always forget what goes in front. Here we go. Beautiful. Okay. There it is. So this is the formula for. Did we actually try to graph this in a calculator? We did, didn't we? Yes. So I had you guys tell me a mean and standard deviation. I put that formula in the calculator, and it spit out a normal curve, which is really cool. I'm glad Past Jeff did that. So if I take a data value, subtract the mean, divide it by twice the variance, and I do that for every possible data value, it will kind of create that curve. Okay, maybe. Now, this very similarly, this is not gonna. Okay, so here's what this guy looks like. Let's see if this makes sense. If I take a sample, so I have a population, and let's say I take a sample and I calculate S. Sigma exists, correct? If I have a population and I'm talking about something numerical, then the standard deviation exists. You guys all agree with me, okay. And when I take a sample, I can calculate the standard deviation of the sample, which we all pretty much agree won't be the same as that. You guys with? If my sample truly is random and it's kind of big enough, shouldn't I expect S and sigma to be close to each other? Yes, okay. So here's something interesting we could do. What if we take the variance of our sample, so the standard deviation squared. There's going to be something else that goes here, so leave some room. Divided by the population variance. If they were the same, that would obviously come out to be 1, correct? Okay. Then what we decided to do is we decided to scale this up by the degrees of freedom. Now, there's a lot more that goes. I just said decided to. It's not quite true. There's a reason we did that. There's a lot more behind the scenes here. I'm trying to give you an elementary introductory level explanation. So I go take a sample. So how did we create this picture? We took a sample of people in Florida, we got their average age, and we plotted it. And then we do it again. You with me? So how would I create the picture for this guy? I would go take a sample, get their standard deviation, and divide it by get their variance and divide it by the population of the variance of the population. And then I would plot that point. Okay. Maybe. Okay. So what this picture ends up looking like for n greater than 2, this is the first example. Let me ask you, this picture, it's skewed what? To the right. Skewed to the right. It always looks like, which direction does somebody pull the taffy? So you got a big mound of taffy. Which direction does somebody pull it? They pull it to the right, so skewed to the right. I affectionately refer to it as the job of the hut, but you know, it's for me. That is what it would look like if I actually did what I just said. If I take every sample of size 3 and I do this work and I plot it, it will end up looking like this. This actually has its own formula. I don't think this book gives us that one. It's sort of like that, right? But again, you've got that formula versus the z-score formula. So if I just make a z-score for every possible, let's say, sample, and plot them, it'll be this, if n's greater than 30. If I do the same thing with standard deviations, it'll be this. So one big thing I want you to understand, it makes sense the picture won't look the same, because what is one thing that kind of governs the shape of this is the standard deviation. So if I plot standard deviations, why would I expect it to look like that? There's no reason it should look like that, because it actually tells me what this thing is shaped like. So if I have a bunch of those, why should they be shaped the same? So, but it doesn't explain why it's shaped like this. But again, this is sort of like empirically done, yes?
Is it always skewed right, or can it be skewed left too?
Always skewed right. And the larger the sample size gets, the more this kind of pulls out, and then the more normal it becomes. I think the book shows pictures of that. Yeah. So this is degrees of freedom equals 2. It actually looks like this. That's why I said greater than 2. Oh, degrees of freedom greater than 2. It looks like this. For degrees of freedom equal to 2, it looks like that. But would a sample size of 3 be a good thing to base anything on? No. Okay. So this is what they normally, and look, it already looks a lot more normal, doesn't it? Just at 24. So just like sample means or something, if I get the sample size big enough, it starts to look normal. Same thing happens with chi-square. Yeah.
It's kind of like how with NP and NQ, you're giving it enough room on the left and right to kind of become normal. Is that kind of?
Sort of, yes. Not exactly that, but it's related to that. Yes. And again, there's a lot more behind the scenes here, but okay. All right, let me stop for a minute. So z-scores kind of determine this, and they are reconstructed by, for example, getting sample means and normalizing them. Chi-square scores, most of them look like this, and they're constructed by taking sample standard deviations and normalizing them. That's the comparison. So chi-square is like a z-score, but they work for standard deviations. Maybe. Do you see how this is a little weird, but z-scores compare sample means to means through subtraction. That's true. Whereas chi-square compares sample standard deviations to population standard deviations by division. It's again, I feel really bad, but there's a lot more math to this. If you took a calculus-based stats course, then you get a solution. We don't need all that. Does everybody feel right now, what you're probably thinking is, what the hell am I going to have to do? Okay, we're getting there. Okay, I understand that. But do you understand the analogy here? That I wouldn't expect this picture to be the same, because it's graphing standard deviations in a sense. Can you guys tell me what this peak should be?
The mode standard deviation.
Yeah, well, the modal chi-square, right? So what should happen the most, if we take really good samples, more of these should be close to this. So this should be hover around n-1, the degrees of freedom. So this peak should be around n-1, whatever that is. Notice something else. Can anybody figure out what the smallest chi-square, what's the smallest z could be? Is there any smallest it could be?
0.
No. Smallest, can't z be -1? Right, that's one step down. How small could z be? Theoretically, you go forever, right? What about chi-square? Look, if I calculate an s, right? Assuming sigma is not zero.
Oh.
Then I wouldn't do anything if sigma was zero. What's the smallest chi-square could be is zero.
Because, in the graph, it looks
Because
like
these are
it was-
variances, the small, in fact, even if it wasn't squared, what's the smallest the standard deviation would be?
Zero.
Zero.
Is that because, like, on the graph you showed earlier, if it was like a sample size of 2, it was like the actual y-axis was like an asymptote of the graph. It was kind of
Oh.
oscillating. It was,
Yeah. You mean here?
Yeah.
So what are you saying?
I was saying that like it's theoretically like approaching 0 the whole time.
Oh, this side.
Yeah.
Yes. Yeah. All right. Things get weird for small sample sizes. They just do. Okay. All right. So, in terms of what we're going to need to do, you don't need to know every detail about the concept, but I want to at least lay some groundwork down. Now, this is the picture for chi-square. This is one way to get chi-square. This is basically the most essential way to get to chi-square. There are, just like there's more z-score formulas than that one, there's more chi-square formulas than this one. Let's see. Okay. I've made a decision. So let me show you something you could do. Can you guys, how would I solve this for sigma squared?
Multiply by sigma squared both sides.
And then divide by chi squared, is that cool? So if I solve this, for sigma squared, I get that, right? I could then, if I take a sample and I get a standard deviation, so I take a sample size n and get a standard deviation s. What was the immediate thing we did? If we take a sample and we get a sample mean, how did we improve on that?
Increasing the sample size.
No, I mean, change nothing. If I just say the average grade this person gave was a C, what's some other information I would like to know?
Oh, standard deviation.
The spread. What's the immediate thing we did? Let me just say, we built a confidence interval, right? That communicates a lot of stuff to us. If I construct a confidence interval, that communicates to us a lot of stuff. So if the confidence interval for grades was B to D versus A to F, we had that whole discussion earlier this semester, right? So if I get a standard deviation from my sample, I'm curious what sigma is. Right? I want to know. Wow. Look at the chart. I want to know what the population standard deviation is. Is that cool? Just like if I take a sample and I get a sample mean, I kind of want to know, okay, what does that tell me about the real mean? That's what confidence intervals do, correct? It gives me some feel for where the mean might be. Okay. Now, let's say, so here we got this shape, right? Let's say that n is 31. Okay. And I want to create a confidence interval. The beautiful thing about z-scores, whenever I make a confidence interval and it chops the middle off, aren't they basically the same number? One's negative, one's positive? Of course, right? Because they're symmetric around 0. Are you guys with me? Is this symmetric around 0? What's this?
Pretty steep.
0. That's the smallest it could be, right? If I get a chi-squared of 0, that means the standard deviation of the sample was the same as the standard deviation of the population. Yes? I'm sorry. That means the standard deviation of the sample was 0. Okay. Thinking about something we're going to talk about later. So if I want to construct a 95% confidence interval, it's not going to be symmetric. Do you see that? Maybe? Okay. So we're going to need, if I wanted to construct this, I need to figure out values of chi-square. I need to look at what I'm doing. I need a chart that I can look up values of chi-square so that I can start to construct a confidence interval. So, for example, let's say I want to be 95% confident. How much is outside of the tails then? 5%. So that much we keep. That's something we, not 5%, 2.5%. That's something we keep constant. We want to capture the middle 95, but it's not going to visually be symmetric because the shape is not symmetric anymore. It's got a big ass tail, right? Okay. So I want to have a chart where I can find out what these chi-square scores are. All right, so let me give you the chart. Where did I put them? Oh yeah, here we go. All right. One more chart to keep track of. You're welcome. Yeah, she'll do it. Now, I will say this. It is like some kind of evil. It is evil. It just is. There's no other way around it. The z-score chart tells you the areas that are to the left, correct? Okay. Chi-square. If I kind of zoom out a little bit. Areas to the right. Okay. So just, math people, we can't, sometimes we just can't contain the evilness. It just spills out. There you go. Okay. So somebody help me out. What area is to the right of this chi-square? I've got it up on the board. 2.5%, 0.025, right? Do they have a 0.025 column? Yes. One nice thing about this is basically you could put the picture on top. I want this to make sense. Do you see how there's like a bigger chi-square and a smaller chi-square? So the bigger one's going to be over here, the small one's going to be over there. You guys kind of with me? A little bit? Not at all? Okay.
So this chart is like skewed to the left?
No. It's still skewed to the right. It's just set up to kind of mimic.
Okay.
Here's 0 and here's all the way out here. Right?
Got it.
All right. So 0.025, the chi-square. What's my degrees of freedom? Degrees of freedom. In this case, it would be 30, right? Okay. So if I go down, 0.025, stop at 30, I'll get 46.979, right? So let's put that down here. 46.979. So help me out on that one.
Negative 46.979.
Again, there's 0.
Oh shit.
Oh shit. So how am I going to look at this guy? Again, how do we look at this guy? To the right of him was 2.5%, 0.025. What's to the right of this guy?
97.
97.5, so 0.975. So again, what's beautiful is, look at this. At least the areas are symmetric. Do you see that? If you look there, you look there for the other side. So then if I stop at degrees of freedom of 30, 16.791. Those are like z-scores. So if I, for example, let's see if anybody remembers this number. If I want to make a 95% confidence interval for means, what would the z-scores be for 95% confidence? Who remembers?
1.645.
1.96? So negative 196 to positive 196, correct? Bless you. Would that be the answer? If I'm talking about the amount of time it takes somebody to find a parking space, would it be negative 196 to 196? That's our number of minutes. Some people take less than, think about negative 2 minutes. No. I would then have to make those back into raw scores, correct? Okay. So this is like, I'm at the level where I know a z-score. In this case, I know the chi-square, but chi-square is like z. It still tells me where I am. Do you see how the chi-square tells me where I am in this picture? The same way a z-score tells me where I am. You're not even looking. I don't even know if you're looking yet. So I use this formula to convert each of these into a variance. So let's say that we get S to be, let's get a standard deviation of 17, right? So we take a sample of 31, let's say we take a sample of 31 students, and we get a standard deviation in their ages of 17, no, in their test scores, 17. You guys with me? I'm curious. So that's just a sample. I'm like, okay, what does that mean about the population standard deviation? Where could that be? The same way we take a sample mean and we're like, okay, what does that mean about the actual population mean? We make a confidence interval, right? So how would I make this into an approximate variance? I just use a formula. N minus 1 times S squared divided by chi-squared. Oh, n minus 1, what is that? 30, right? Sorry. So somebody help me out. It's going to be roughly... I don't know. 500 and something. I think it's going to probably be 527. It's almost definitely wrong.
$516.
516? Point blah blah blah?
348.
Okay. Do a square root of that real quick. Let's get the, because that's the variance, correct? So we do the standard deviation, we're going to get the square root of that. It should be like, come on, math boy. I don't know, 23, 20, that's way off.
22.72.
Oh, holy shit. 22.72? Something? Okay. Okay. And then if I make this into a variance first, I'll do the same formula, 30 times 17 squared divided by this guy. Let's see. Oh, I could approximate that. Ooh, 3, so that'll be 172. So it'll be a little bigger than that, so like 184. What is it?
184.5.
Holy shit! Oh, I'm sorry. I apologize.
On fire.
Look at that. I'm sorry. It's my one skill. I have to, you know. So 184 point blah blah blah. So what's the standard deviation? Take a square root. 13.5. So we would say that we got 17, but we would say that the confidence interval is 13.58 stuff up to 22.72 stuff. So that does the same thing that a confidence interval for a percentage or a mean does. It gives a better feel for how sure we are about what we got. So the population standard deviation, we're 95% confident that this interval catches the population standard deviation. I love it. Okay. So this is one type of problem you can do with chi-square. And so it accomplishes the same kind of stuff that z-scores did for means and percentages. chi-square lets us do the same kind of stuff with standard deviations. And again, the distribution is a little weird. It has a hard wall at 0, all this kind of weird shit. Yeah, let me try to do that. So that's one example of one problem you could do. Now, here, I'll say something that's going to really make everybody angry at me. We're not going to do this kind of problem. But, I love it. Don't you love it? You're like, I want somebody to take their notes and shove them, throw them at me. No, don't do it. Philip's like, I'm thinking about it. I needed to go through this problem because I want to connect chi-square stuff to stuff we know. It'll really hammer home what chi-square's job is. It's the same job as z. It tells us where we are. All right, math boy, let's do it. Okay, let's do a problem we'll actually do. Okay. Let me tell you this before you get really angry at me. The section I made extra credit is hypothesis testing with chi-square scores. All right, is your anger level coming down? Okay. All right. There's up here, John.
Excellent, what's up?
Yeah. Show me the whiteboard. Okay. Wait, your own damn car. All right. So, I don't know how much that was actually recorded. So there's another, just like there are multiple z-score formulas, there are multiple chi-square formulas. Every chi-square formula will construct chi-square values that fit into the picture. Just like every z-score formula constructs values of z that fit into the picture, right? Everybody with me? Okay. So here's the next, let's do this. Before I forget, get myself in trouble. Let's see if I can get myself in trouble. Somebody do the square root of 3.841 for me. Before I forget this.
1.9598.
Round that to 2 places. What do you get?
1.96.
Does that sound familiar?
Oh,
Does that sound familiar? Somebody do the square root of 5.02. Well, let's see, which one will work? 6.635. Do the square root of 6.635. I think that's a good one.
2.58.
2.5,
75.
2.575, 2.576. Does that sound familiar to anybody? That's like a 99% confidence interval, right? So, real quick, this is one little thing. For a single degree of freedom, chi-square scores, here's the reason they have a square in the symbol. For a degree of freedom of 1, chi-square scores are the z-score value squared. It's like I take a normal distribution and I fold it on itself. That's all I'll say. I just want to. There is a connection between chi-square and z-scores. And it goes a lot deeper than what I just said, but it's the most immediately obvious thing you do. If I square root these, I get back to z-scores. So it's like I fold a normal curve and I multiply the z-scores when they overlap. And then I get this. Kind of crazy. Okay. Anyway, okay. Just a neat little thing that has a lot of other implications. Okay. So here's the other type of test, and let me say this. How do I want to do this? Yeah, I've already got that kind of problem. I don't know how to do this in problem. All right, let's say that. Yeah, we expect the following distribution of, you can come up with something, Jeff. You can do it, buddy. Sure. Of pets. Number of pets owned. Okay. Yeah, sure. Okay. That'll work. We expect, let's see. Let's put 30%, 40%, what's that? Okay. 20%, and 10%. Okay. So we have an expectation of how data values should be distributed. Now, you could probably come up with a better example than the number of pets people out there. You go into a situation and you're like, okay, they should look like this, right? So if I go to, a better example would be, I expect this distribution of cancer occurrences in towns. And if I take a bunch of towns around some factory and what I see is far off from what I expect, that is evidence something is affecting cancer rates in that area. Are you guys with me? So we go in with an expectation and then we check to see how close reality is to the expectation. Okay. Now, so we could even have done that, but let's talk about pets instead of cancer. I think that sounds better. So if we sample 200 people, what does this translate into in terms of, actually wait a minute, let's do it this way. And we see, what do you got, Jeff? 58 have no pets. You can do it, buddy. You can do it. 85 have one pet. I'm really doing this horribly. I'm sorry. 35 have 2 pets, and then what does that leave? What does that leave? Let's see. 143, 178. What did I say? 200. So 22. Somebody check me. 22 have 3 pets. Do these add up to 200? Can somebody do that for me? Trust myself. 143, 57, 200. Okay. So far, nothing amazing. So we went and talked to 200 people, and we see this. Now the question is that evidence that this town does not follow this expectation? Do you guys with me? So let's do this. Let me kind of get this together. So we have values. We have observed values of each, right? Observed 0 pets would be 58, 85 had 1, 35 had 2, 22 have 3. That's the observations. So in these kind of problems, I have to just tell you the observations. All right, nothing amazing so far. I just tell you. 200 people, we see this. Okay, you just copy that shit down. Now, can somebody tell me the number of people we expected to have no pets? How many people did we expect to have no pets?
60.
How did you get 60?
30%.
Yeah, we expected 30%, and we took 200 people. 30% of 200 is 60. So keep going. How many did we expect to have 1 pet? 80. 2 pets? 40. And 3 pets? 20. Now just look at it now. Do they look close?
Yes.
The same way if you said, well, I think the mean is 12, and we got a mean of 12.6. Are those close?
Yes.
All right. Now here's where I understand the answer you just gave. Now think about it longer. What do you not know that doesn't tell you if it's close or not? Is 12.6 close to 12? Most occurrences we would say yes. What does it depend on? What if the standard deviation is 0.1?
Then it's going to be
12 to 12.6, how many steps is that if the standard deviation is 0.1? 6 freaking steps, a z-score of 6. Everybody in here should go, holy shit. Again, that's like a 40-foot tall person. Z-score 6. Not really have to do the work, but anyway, it's like a stupid tall person. Yes? It's with me. Okay, so, yeah, those look close, but that's not good enough. Is it a very big sample we took? Well, 200 people, yeah. But how many possible categories are there? Here's where you guys are going to really love shit. Do you guys remember? What's the formula for the degrees of freedom
N-1.
so far? Up till this point? It's not that big of a deal. So in these problems, the degrees of freedom will be the number of categories minus 1. So how many categories did we have? 4. So in this case, the degrees of freedom are going to be 3. I love it. And by the way, I might as well tell you, see if this name makes sense. Aren't we trying to see how closely the observed values fits with what we expected? Is that like a normal way for me to say what we're doing? What we see, how closely does it fit with what we expected, correct? So the name sounds goofy, but not as goofy. Now, these are goodness of fit tests. Goodness of fit. And again, math people, they're not English majors, so goodness of fit. What? Fit good stuff. Okay. I'm allowed to make fun of this because I am one. So let's see if this makes sense. If we're trying to see how closely observation meets with expectation, what's the first thing I should do? How did you tell that they were close? Because in your head, what did you do? How far off are these?
50 over 60.
No.
Oh.
How far off was this from this? If I got 60, would that be any far off?
No.
No. So how far off is it? 2. Yes? Okay. So you remember doing like calculating standard deviation and we took the difference and then we had to square because we didn't want any negatives? Remember that? So we're going to basically do the same thing. We're going to do observed minus expected squared. Let's see if we can do that more directly. So it makes sense. If I want to see how well this fits with what I expected, let me take the difference between what I see and what I expected. That hopefully just makes freaking sense. I'm squaring it for the same reason we squared standard deviation stuff. I don't want any negatives to mess me up. So 2 squared, 4. 5 squared, 25. 5 squared again.
25.
And then 2 squared again.
Oh.
Neato. Now, let me ask you this. Oh shit. If I have $5.80, how much does finding $20 mean to me?
Wow.
I'm talking about I have $5.80 in the bank. So if I write a check for $6, they're going to charge me $25 I don't have because of overdraft fees, right? So if I have $5.80, how big is it for me to find $20? Huge, right? Huge. Okay. What if I have $5.8 billion? Does $20 change my life as much? No. So this squared difference, how relatively big it is what's important here. I really want to, so if it was a difference of 4, but these were on the order of billions, that doesn't mean shit. But if these were like on the order of 0.1 to 0.2 or something, 4 would be huge, yes? Okay, so what we do then is we kind of standardize these. We take our observed minus expected squared and we divide it by the expected to get a feel for what's the relative, how large are these differences relative to what I saw. Does that make any sense? Okay. Because a difference of 4 means something more for this than it does if these were in the billions. A difference of 4 wouldn't mean shit then. So then I want to take everything we did divided by the expected. And can you see how, if this is list 1, this is list 2, this will be list 1 minus list 2 squared. Believe it or not, I have a handout. And I have all this shit on there, so I know, it's crazy. I figured I'd try that. And this is list 1 minus list 2. This will be list 3 divided by list 2. You see how I can do all this work in the calculator? Right? So what is 4 divided by 60? What would that be? 4 thirds, 25, 23rds, 60. No, I can't do work in my head. Oh, wait.
666.
What is it?
0.066.
Oh, it's close. Okay, 6 point, yeah, I had the decimal wrong place. So 6.7 roughly, right? Or, I'm sorry, 0.067, yeah. Is that what you said? Okay. Roughly, if you round, okay. Is everybody with what's happening? 25 divided by 80. 0.3125. 25 divided by 40 is twice that, so it'll be 0.625. Check me on that. And then 4 divided by 20, that's easy. 0.2. Okay. So, we had this formula for chi-square. I almost wrote the new one down. That's just like a z-score of x bar minus mean divided by the new standard deviations. Then we have another formula for chi-square, which, thankfully, is this. You have a picture that for degrees of freedom bigger than 2 looks like this, right? When it gets smaller than that, it gets crazy, but oh well. That this fits into and this fits into the same way that z equal to p hat minus p over square root of pq over n fits into it, like x minus mu over sigma fits into it. Guys with me? So the picture exists and there's multiple formulas for putting values into that picture. Okay. So what do we get? So that all that means is I just add the last column, right? So can somebody do that for me? 1.8045. Okay, now, so this is like z star. Did we calculate this based on our sample?
Yes.
Okay.
Chi-squared star.
Huh?
So like chi-squared star, is that what we call it?
Sure. I think I tried to do that once and it just, it's too much shit going on. But this is like z star because it's what we calculated. So what's missing then? I have to compare this to something, don't I?
Yeah.
So let me ask you this real quick. So I'm saying that this still fits into this picture. And remind me, the degrees of freedom was what again? Anybody remember? It's not 199, right?
3.
It's actually now, you're gonna love this,
Oh, it's 3.
It's the number of categories, right? What letter does category start with?
C.
K, that's right, so.
Nice.
Just pick, I don't know. Okay, it's not only this, but I'd love to make that judgment. We're math people, we don't spell shit. K meaning category in this problem. You understand there are a lot more situations that use this. The same way there's a ton of situations that use Z. But we don't have enough time, we're going to cover this one thing, right? So degrees of freedom here was 3, yes? 4 categories, so degree of 3. What would have to happen here? What's the only way that I could possibly get 0 for a chi-square?
You have 1 category.
No.
Oh, if
I only change my observed. How would I get a chi-square of 0?
if the sum. Oh.
Come on now. What's the only way I could get 0? The minute this is not 60, that's not 0, correct? And if that's not 0, that has no chance to be 0 because there's no negatives, correct? So what's the only way I can make this sum up to be 0 is if these are all
The same.
the same as those. Yes? That would that, how obvious is it that that would be not good enough evidence that there's a difference? If they're exactly the same, that obviously. Right, you with me? Was this a sample?
Yes.
They are different, correct?
Yes.
And yet we soldiered on because we know by now samples don't by themselves tell me shit. Not enough. They don't prove anything. But they could show evidence. So not only do if I got 0 exactly, that is so desperately not evidence that there's a difference. But not only do I have to be different, I have to be different enough. The same way with, not only do you have to have a different meaning, you have to be different enough. Rejection region stuff, right? We're not going to do a whole hypothesis test. Don't worry. You're only going to have to calculate chi-square from this, and then we're going to look it up in the picture. So let's do, if I didn't say what alpha was, did I? Did it say what alpha was? No, because I'm a check notes jerk. But what does that mean we use? 0.05. So can you look up real quick? 0.05 degrees of freedom of 3. What do you get?
7.815.
Do it again, sorry.
7.815.
7.815, okay. This is the rejection region. If we got a sample that was here, that is so far away from what would be the same that it's evidence that it's different. Does that make sense? Okay, and again, we're not going to do all 5 steps, don't worry. I just go on 2 things from you. Calculate the chi-square that's like z-star, and then look up the chi-square in the chart. Now, did we make it far enough? Where did we make it? We made it to 1.8045. Is that evidence that the observed did not meet with the expected? Is that evidence that the population is different?
No.
No. That's all you got to say. Not evidence that there's a difference. Right? So we have not shown enough evidence to say the population did not meet our expectations. Okay, maybe. This is so fun, Jeff. Okay. You don't have to do a full-blown hypothesis test. You just have to calculate what's effectively z-star, like the chi-square, and look up the rejection region chi-square and compare them. Evidence of a difference, not evidence of a difference.
Why alpha is 0.05?
Because they didn't say it. Just like in the book, or just like in real life, or just like whatever. If I don't say what alpha is, 0.05 is the most commonly used one, so that's what we use. Yeah. So, here's that handout. Oh man. First problem is about M&Ms. Now I want M&Ms. So there are 2 ways I could tell you information about my expectation. Oh my God. Every sentence is full of words. There are 2 main ways I can tell you what the expectation is. How I did it here was I told you the percentage in each category, correct? So let's look at number 1. In fact, before I forget, I did bring that. Darn it. There it is. Keep my phone alive. Okay. Say hey, everybody. Hey, me. Okay. Hi, future me. Okay. Gotcha. All right. Let me bring you back up here. I'm bringing projector back. Okay. So the first, can somebody tell me in that first problem about M&Ms, how do I tell you what my expectation is? I don't give percentages, right?
Percentage times 10.
No? So we have an observation we make, right? We take a bag of M&Ms, blah, 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 blah. We want to test if the colors are uniformly distributed, so I put that in bold. So I didn't give a percentage. I didn't say we expect 10% red and 30% brown. I said I think they're going to be uniformly distributed. So if we take a sample of 42, I think it's 42, right? So if you add up all the M&Ms, we took a sample of 42. If they're uniformly distributed, then each of the categories should have the same amount. That's what uniform means. So there's 6 categories, right? 42 divided by 6, 7 in each. So I could either, like the second problem, give you a percentage I expect in each category, and then you take the percentage of the total, or I could tell you that we believe it's uniformly distributed, in which case you just take the sample size and you divide it by evenly amongst all the categories. How's that? So that's why these are all 7, because that's what uniform would mean. I love it. Now, if you had a number that didn't divide by 6 evenly, you would just put decimals here, because expectation is related to average, and averages don't have to be whole numbers. So that's okay. I just made this one a nice one. So once we do that, we do all the same steps. 5 minus 7 squared is 4, 6 minus 7 squared is 1, blah, 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 right? So it's exactly the same. The only difference was, how did we fill in the expected? It wasn't taking percentages, it was just dividing evenly. Okay, so what I want you to do, so there's an example of this for you, for future you, when you're doing homework and such. So since we did this earlier, I want you guys to do number 2. We did an example like this earlier. I want you guys to do number 2. And I was really nice here, by the way. I was too nice. Yeah. Yeah. So 20% is 0.2 of these times. Yeah. Kicking us. So you'll the rest. Oh crap, let's see what's that. 3, 4, 5, 7. Is this 53 down here? Is that what you guys got? What'd you get for this last category?
Yeah.
Yay! Okay. Thank you. Sorry, was there a hand? No. Okay. So let me do this in the calculator so you can see how this would look. So watch what I can do. If you go to your list, so on the first list I'm going to put 118, 198. 131, 53. Over here I could do calculations in the list. So I could do 0.2 times 500, bam. 0.3 times 500, bam. 0.35 times 500, bam. 0.15 times 500, bam. How's that look? Is that all right? Okay. And then what do I want list 3 to be?
Parentheses L2 minus L1 parentheses squared.
Yeah, I want list 1 minus list 2 whole thing squared. So I'm going to go up to list 3. I'm going to put parenthesis the observed, which is L1 stuff, minus the expected, which is L2 stuff, squared. Bam! Now, this is not a very large list of categories, so you don't necessarily have to do it in the calculator. Just, you know. Makes it a little bit quicker. And now somebody else tell me, what's L4 going to be?
L3.
Did I have that up here? Sean's other personality has told me. There's no- you're- L3, so this is L1, L2, L3. So L4 is going to be L3 divided by L2. I like it. So I'm going to do L3 divided by L2. And you get those. Now, even just glancing at this, now this one I made just silly. You could just quickly see that there's a pretty big difference, right? So this is not surprising that these numbers are relatively big. 3.24, 15.36, 11.063, and 6.4533. And then I can do this, since it's in my calculator, I can go second quit, I can go to the list, I can go to sum. We've done this before. Sum up L4, right? And I get, what does it say? 36.116. Is that right? Does that make sense? Yes. 36.116, I think I said. What is that I just calculated?
So that's chi-squared.
Chi-squared. Chi-square star, if you want to be so bold, right? So again, there's always a concrete idea you could hold on to. I want to know how closely these matched. So of course I'm going to take a difference. Squaring makes sense because we've done that before. I want the negatives to go away. Getting it to be a relative, that makes sense. I want to know how relatively big that difference is. Now the part that I understand doesn't necessarily make sense is why does doing that fall into the chi-square chart? At this level, all I can say is it does. Just like you accepted p hat minus p divided by the square root of pq over n, that falls into the normal distribution. You readily just ate that shit up. Well, I'm not saying like that to be mean, because it does, and you can look it up and all that kind of stuff, but we didn't see the entire construction of that. I showed you snippets, just enough. So now what do I compare that to? That already seems pretty big. What's the degrees of freedom here, by the way? 3. And alpha is 0.01. So where's my rejection region start? 11.345? Can you guys all find that? And of course, so we're like out here somewhere. So if 0 means there is no difference, I really hope it just makes sense. If we get far enough away from 0, which we totally did, that is evidence there's a difference. So the test itself just shows there is a difference. Everybody with me? But looking at the data, so we would say here, yes, there is a difference. The sample does not match the general pattern. So I'm just kind of copying straight from the claim. The sample does not match the general pattern. Does not match blah, blah, blah. Okay. Looking at this, though. So bad cholesterol. Did I make that distinction? I should have made that. So like LDL is the bad stuff, right? So say these are LDL levels, which is what I believe I intended. I think I got this from actually close to real data. But don't quote me on that. Past Jeff, you never know what the hell he's doing. Do more people have in this secluded area, do they have lower cholesterol? This we see we just showed evidence there's a difference. But then we can go back and see what difference is that exactly? Do they seem to be healthier in terms of cholesterol or not so healthy in terms of cholesterol? So here's what they are, right? 53 people have a very high versus 75 expectation. 131 have kind of a medium high versus 175 expectation. And then more people have lower levels versus expectation. So what does it look like? Does it look like they're doing better or worse? Better, right? More of them have lower levels than we expected to if they match the general population. So this is exactly what happened back in the day when I was a young kid. You had people just guzzling olive oil. Why were there, in fact, recently it's been apple vinegar, whatever the hell it was, for a while. All right, yeah, I know, exactly. Just people just, I'm like, do whatever you want to, cinnamon, all that kind of shit. But back in the day, we saw in the Mediterranean, we saw people, and we're like, well, they're like healthy. And being Americans, we're like, okay, they're walking more. No, come on. What are they eating? Oh, they're putting olive oil in everything. And that's when the olive oil craze hit. Everybody just got olive oil and just was like, oh, I'm going to lose weight. Cook my hamburger in olive oil. You know, and get in my Hummer and drive 500 feet to my friend. Yeah, right? Sorry. But do you understand? There was a difference. And you could see the difference. But this is a surface level. What causes that difference? So here I kind of pointed to a certain diet. And if they eat something very differently, that could be it. But do we just stop there and go, well, they're eating this weird kind of fruit. We should go just add this to what we eat already, and that's going to make us lose weight. What would be the next level? So this is a first level analysis. Does there seem to be a difference for these people? Yes. We've shown evidence that there's a difference. What would we do then?
Correlation. Or then
Now we're at the level of sort of like correlation. We don't know what's causing
now we're looking
this.
for causation.
Yes, so now we could do like take a group of Americans, give one part of them this fruit, and give the other part, have them eat the normal stuff, right? And then we're like, well, that didn't do it. Then we move on, olive oil or the water. We import the water from there. Maybe it's something in the water. Maybe it's, you guys kind of with me? And of course, the reality probably is they actually constructed cities where you could walk to where you need to go, so there's a lot more walking happening, right? Okay. All right. So this goodness of fit is another kind of like initial exploratory statistics to do. And then you come in with some more detailed stuff if you do see a difference like this. Okay. That's it. That's all I've got for this entire semester. So what I wanted to do was devote part of today to review for the final, and then all of tomorrow for review for the final. I don't know if you guys are cool with that, because I could do more. No, okay. There is, I think I put one. We could right now all try to do number 11 on the practice final, right? If you wanted to. Let's see. If you want to take a break, we can. Otherwise, we can just kind of go and then leave early if we want to. It's totally up to us. If you need a break, you can take one if you need one. Do you guys, anybody want to do this right now? And then then we'll let's do this. So we'll do number 11. Or we can leave number 11 for you to do later. I'm sorry. I just want to base it on what you need. We're going to make a formula sheet for the final, which really you just bring all your formula sheets. But it's kind of nice to kind of lay them all out. And then we'll just open it up to whatever questions you guys have specifically. Does anyone want to do number 11 right now? Yes. Okay, let's do number 11. That's all I needed was one person. I will warn you that you got 342 students, correct? Or are you going to get nice whole numbers when you take percentages?
No.
Can somebody tell me, what does this look like? What kind of distribution does it look like it might be?
Normal.
Yeah. This is a rough approximation for 5 categories, what the percentages would be for it to be roughly normal. So we're effectively testing to see if these grades that I see are roughly normally distributed. All right, so if you want to, try number 11. Go for it. If you don't want to, try a different problem out. Or sit there. Yes.
Okay, I have a quick question. You put 205 for the same as this, right?
Yeah. Did I just get back to you? Oh, I'm on it. I love it. I'm embarrassed. Well, I got the spreadsheet right here, so I'll update it.
I just thought I'd let you know.
Yeah. Okay. Yeah, if you guys see anything wrong on the grade sheet summary, if I say I'm missing something I'm not, if there's a grade that's not right, I've got the spreadsheet right here, so I can change it.
That's correct. There's some kind of miracle in getting everything done in July. Then,
Yeah, doing corrections in this obviously is huge. Yeah.
yeah, this one happened. Something.
One thing I could do is just leave this blank. Right?
You gave it to me, so.
Well, you missed this one, so whatever you make on this one's in place of this, right? But, I could do that. But yeah, so you're gonna wanna make corrections to the test primarily, do as much homework as you can. Any of that's gonna immediately up your grade, plus get you more ready for the final. Yeah. So at least this doesn't say like, you know, some people might have it saying 108. So, you know, even with all the extra credit, they couldn't quite get there. Some of you guys, it might say a negative score you might need to pass, which is always neat. But like hit you with the car on purpose twice, while you're negative. Don't take that as don't test that, by the way, please.
Scared?
Hmm? Yeah, and I'm not gonna walk near you guys if you're in your car. Okay. Oops. Blush. Okay, good. Ah, okay. Are you guys getting these kind of numbers here for? Does that look at all familiar?
Yes.
Great. So this is the observed minus expected squared. And then this is the observed minus expected squared divided by the expected. Now, I could be wrong. I'm seeing a lot of people looking confused. So let me double check what I've done here. That looks good. Looks good, okay. Did you guys get these numbers for list 2, the expected? 13% of 500, 20% of 500, and so forth, right? Okay. So, on the surface, there seems to be a decent difference here, right? There were more A's, fewer B's, more C's, fewer D's, fewer F's. So it looks like there's a pretty decent difference between the two, with the observed and the expected. But when you add these up, and again, the quick way to do that is to go to list math sum L4. I get 6.975. This is chi-square star if you want to. Did I tell you what alpha was?
No, so it's assumed
0.05. Degrees of freedom is what?
4.
1, 2, 3, 4, 5, minus 1, 4. I like it. So it's not 341. So when we're doing a goodness of fit, it's the number of categories that matters. So if I look that up, 0.05, 4 degrees of freedom, I get 9.488. Did we make it far enough away? No. So there is a difference between the sample and what I would expect, but that's not a big enough difference to show evidence that the population is different than a normal distribution. Okay, maybe. So then, does this group follow the expected pattern? We did not find evidence to say they don't. So I would word the question better for you because it's a little worded poorly. Because you never accept the known blah, blah, blah. Don't worry about it. So we did not find evidence to say they don't follow the expected pattern. So again, if I make it in here, evidence of a difference. If I don't, not enough evidence that there's a difference. Okay. Yes?
How did you get the alpha value or the alpha?
If it doesn't say, just like in the book, if it doesn't say what alpha is, we assume it's 0.05. It's just the most commonly used one. Yeah. It's sort of like, guys, real quick. Little side note that doesn't mean a damn thing. What does that symbol mean? Cubic root of 8, right? What does this symbol mean?
Square root.
How do you know it's a square root?
Because
When there's nothing there,
it's assumed.
we know it's a 2 because that's the most commonly used root. I don't know if you guys ever thought about that. Putting a 2 there just looks weird even, right? I don't know if you guys agree with me. But it's the most commonly used root. Math people are lazy, so we're like, why put the 2? It's just the one we're going to use all the time. Same thing here. When they don't say alpha, 0.05 because it's the most commonly used alpha level. Okay, so let's do this. How's that? Is that decent?
Yeah.
That's not bad. So you know the chi-square distribution exists. You kind of have a feel for what it's supposed to try to do. You kind of have a feel for why it looks different from a normal distribution. And I've told you there are an insane number of uses for the chi-square. Insane. So this we looked at two, sort of. We looked at the confidence interval, which you're not going to have to do. And then we looked at the goodness of fit, which you're going to have to do. Okay. So let's do this. Let's make the, pretend like there's an earthquake. Let's make that the formula sheet. And then you guys can ask however many questions. And if you feel like I got to get this shit out of here, then we got tomorrow still for more review, right? So let's make this ultimate, all-encompassing, one formula sheet to rule them all kind of thing. Okay. So. Whee! First chapter. No formulas, right? First chapter, our favorite chapter, it was just definitions. I'm being facetious. Second chapter. We get mean, we get median, we get mode, we get percentiles, box plots, we get histograms, we get C-cell, we get standard deviations, right? I don't think did I tell you this? I'm not going to make you, remember this formula? Yes? Okay, so once we got out of chapter 2 and got past the first test, I'm not going to make you do this formula again. We're just going to get it from one bar stats, which we've already done a few times, right? Because now it's sort of busy work. So the reason I do this in the first place was just to get a mental feel for what goes into calculating S. So now we can get S out of a calculator, but you have a better connection to it, is my hope. So don't even put that on the formula sheet, right? So chapter 2, no formulas to write there. You have to know class width for histograms. You have to know how to get the mean, the median, the mode, right? Nothing major there, stuff like that. Okay. I'm not going to ask you to calculate standard deviation for listed data. You can just do that in the calculator if I do. So chapter 3, of course, is probability. You know, and real quick, I know we have this on a formula sheet already. I just feel like it's good to do this on the review day, because as you see them, you start to kind of go, oh yeah, how the hell do I do that? Oh yeah, what the hell, how did you use that? Is my hope. Okay. So of course the and one is weird, it's got two different ways to calculate it. Yes.
I was wondering, what was the line for the sentence?
Oh yeah, what does that line there mean?
Given.
Given. So the probability of B given A.
I was saying when I put it in the calculator, how would I put it?
Well, if you have to calculate it, here's the formula for it. Yeah, you can't put this in the calculator. You have to either know what this value is or have a way to calculate it. Yeah. So that's chapter 3. Chapter 4, there's the x, p of x stuff, and then the binomial stuff. That was discrete distributions. So you have like the mean is the expected value, exp, remember that? Yes, Jeff, that was very creative. Okay. And then you have the variance is a little bit worse, as it always is. Does that look at all familiar? And then you have the best formulas ever. Well, first off, let me do the probability formula for binomial. And then you have the best formulas for the mean and the standard deviation that we've ever come up with. Can you guys all see that? All right. So that's chapter 4. Chapter 5 is uniform. There's no real formulas there. I'm not going to make you do the mean stuff. You just have to know how to draw the picture, calculate probabilities. No formulas for that. I'm not going to let you write down area equals length times width for a rectangle. Got to know that. Chapter 6 and 7 were where we started doing stuff more directly with normal distributions. So that's where we have, this actually came up earlier, but it makes sense to put it here. It's where we get this guy, and we get this guy. That's chapter 6, and then 7 gives us this guy, and this guy, and this is what would become Z star in hypothesis testing. So that's chapter 6 and 7. Let me think if I'm missing any. 7 is all, no, that's 8, okay. Very color coordinated today, Jeff. Does orange show up? Let's see. Chapter 8 is where we did, is that all right? Confidence intervals, right? When do you have to use a t-score? Yes, and of course this formula, these formulas tell you, right? And of course, this is what we borrowed to construct the Z star formula for testing percentages, right? We'll see that in a minute. And then, of course, you've got the associated formulas for figuring out how big of a sample you need. So I'm just going to put them right next to each thing. It makes sense. Okay. Don't know if you guys can all see that. And then finally we got chapter 9. The only thing chapter 9 really introduced was this guy. It was the only new thing. And that's where we stole standard deviation from this guy. 10, if you want to, you can put that formula down for the extra credit section. I was kind of happy a few of you guys did the extra credit on the test and got it right. That was nice. Let me think. So that's really the only thing. I mean, chapter 9 uses, like I said, this guy. If you want to, you could put down T star. Just to remind yourself, because some of you guys still don't do this all the time, you have to still divide S by the square root of n. All right, so some of you guys didn't do that. I think that was on, I can't remember which test it was.
So you said the area in black was which one?
The who what?
The area in black was which chapters?
The area
middle one, top row.
Here?
Yep.
What about
That area you just worked out, that was, which chapters?
area? Oh, you mean this region?
Yeah.
Oh, I'm sorry. This is chapter, let me look at it. Chapter 7. Chapter 6, chapter 7. Yeah.
So that, just, the top one is chapter 6, the rest.
Chapter 6, yeah. Chapter 7.
Got it.
Cool. And then, let me think. So that's chapter 9. Chapter 10, you can put that formula down if you want to. Chapter 12, there's no formulas. That's the do it in the calculator and show me the scatter plot and line of best fit. And then chapter 11, we got this thing to worry about. That's the new one from today. Okay. Wowzers. Look at all that stuff we never even knew was out there. You're like, okay. Could have gone without knowing. That's okay. Anything you think I left off of there, by the way? Like some of you guys are like, that's plenty, man. All right. Because I'm open to it. Okay, so this is all the formulas you can have. Yes.
For test 1, we had on the formula sheet, we had formulas for variance and for sample populations. Earlier I did hear you say something about using 1 bar stats to get that set, so it's busy work. Just double checking.
Yep.
Okay, that's okay.
Yeah.
Just wanted to.
Once you're past that first test, then we have more to worry about besides just calculating S by itself. On the first test, that was a problem by itself. Now it's like, you've got to know that so we can do all this other shit. Yeah. Okay, so you've got the practice final. I'm going to have the answer for you tomorrow. If there's something you want to do right now, we can ask questions. You can ask questions from homework, from the practice final, from any test, from any quiz, from the last test, anything. It's wide open. And of course, we still have all day tomorrow to do even more. Yes.
I don't have
You don't have what?
practice final.
Practice final. Okay. Anybody else need the practice final?
Professor?
Yeah.
On test 2 on our formula sheet, we have another formula for z-scores. X minus x bar over s.
Oh yeah. Well, yeah.
We're gonna use that at all on the final?
No.
Okay.
Yeah. Because then we got more refined, and now we understand that would be more of a t-score.
Oh.
But in the early going, there were some problems in the book where I think they did that, where they used a standard deviation from a sample to calculate a z-score, which now we know better. It's sort of like unusual was 2 steps, and now we've gotten more refined. Now we understand that it's doesn't always have to be 2. Yeah.
Chapter 9 is the work, right?
Chapter 8 is confidence intervals. Chapter 9 is hypothesis testing.
Got it.
Yeah. How do you guys study for the final?
Traditionally, because a lot of classes give me, the math class at least gives the practice final. I really just go based off, that's the big one. I go over that, looking at if I understand each problem, can I do them, and if we have an answer key, it's like try and compare it to, okay, where did I mess up? Just try and understand each problem, how
Yeah.
to do them, you know what I mean?
To me, that makes sense. Since I've given you, and you don't always get something like this, this is a good kind of like surface level. So if there's anything you have a trouble with, then you try to figure out what section it's from, try to figure out what handout relates to it, whatever. Then you go to those sources to kind of get more practice, right? Is every single thing that could possibly be on the final on this piece of paper, you think? No. But if you're able to do the practice final with relatively few snags, you should be relatively ready for the final. So the next level of studying that you could do is looking at old tests. Because that kind of shows you the kind of problems I like to create, because not everything that's been on the test is represented on here, so that's like the next level of what kind of problems could this guy give me, right? Yes?
Can we just go to 2 from test 3?
All of 2 for, yes, hold on, let me see. I want to remind myself, I like to do this, I think I made this and I just remember to put it up, like a checklist of sorts. I can't remember, I think I did create a checklist where you kind of go down and you see the concepts from every chapter is there, and you're like, do I feel good about this? Check. How about this one? I don't know. So then you can kind of, that's another way to sort of figure out what to focus on, right? So you said number
Number
2. Oh, okay, so what I'm going to do to make it fair, so that I'm not doing just for the people that have that one version, I'm going to make a problem pretty much exactly like it, right? So everybody got all the formulas you need? Okay. I think this is the most colors I've ever had on a board at once. Oh yeah, where's that dude? There he is. So let's say we feel that band, that's going to be that at most 40% of students in this course will remember concepts in a year. Okay. I don't know, just making something up. We sample, well, not this course, but like all the stats courses being taught this summer, which is give me a bigger group. We sample, what do you got, Jeff? Let's say 68 students, and find, you can do it, buddy. Can I? And find, shit, I gotta make sure it's, give me a moment. 6.8. 6.8. No, check. Yeah. Just, yeah, it's okay. It'll be okay, man. Oh, okay, that was not too far. Find 29 retained information. I think that's about right, yes? Yeah. What did I say, 68? Yeah, good. Okay, we're doing okay? Okay. Test the claim using alpha equal to point, what do you got, Jeff? 0.1. Sure. All right, so step 1, what's the claim?
Claim is probability P is equal to, or sorry, less than or equal.
Less than or equal to?
0.4.
0.4, good. Okay. So where would that go?
No.
In the null. So what's the hop?
P is greater than 0.6.
No.
Point 4. Oh, man. Then we can kind of lay out this sample information to kind of get a good
So 2, Z or nothing.
Z.
Why?
Percentages and
What's N times P?
or we have to find P. 40% of 68.
0.4 times 68.
That's gonna be like 20 something.
That's true, it is 27.
27.2.
27.2. And that is greater than equal to 5. And then NQ, 0.6 times 68.
40.8.
Was it 40? 0.8, that makes sense. Greater than equal to 5. Check, so we can use Z-scores. If it wasn't, then we could use
Nothing.
nothing. Good. Try to trick you, I couldn't do it. Rejection region. How many tail tests is this?
One.
One tail. Where's the tail gonna be?
On the right.
Up. Alpha is 0.01. What's that Z-score? Yay, cool. Okay. So if Z star is greater than 2326, what can we do?
Reject it all.
Reject
Support the all.
the hoe, support the hop. Okay. So what are we talking about? What can we use to talk about it? Where does evidence start? Did we find enough evidence? Step 4 is going to be, and it's very red up here now. Step 4, what's P hat?
Point.
Where are you getting it from?
29 over 68.
Good, 29 divided by 68, so it's just the percentage from the sample, that's why it's got a little hat on.
0.4265.
Kick ass. By itself, is that already evidence for hop?
Sure.
I mean, if it was 0.36, we wouldn't even keep going. Do you understand that? If I got 0.36, I wouldn't even do any of this shit. Because that would never be evidence that is greater than 0.4. Now, real quick, which one, considering what we feel, which one are we actually sort of, not really rooting for, because science doesn't really do that, but which one is us?
Oh.
We're the hoe, right?
Oh.
We're the, aren't we? We
Oh.
feel that at
Oh,
most.
right.
That was the claim. Okay. So we are the null hypothesis. So we, in a way, we hope not to get in the rejection region. But again, hypothesis tests always try to disprove HO, try to reject it, try to support this. We could be rooting for either one. It doesn't affect how we test things. So now I can make the Z star, which is P hat, minus
B.
P, which is
0.4.
0.4, divided by the square root of
PQM.
0.4 times 0.6 divided by 68. It's gonna be pretty big. Too bad, Jeff. What's gonna be? It's like 0.5. That's like 8. Good Lord, Jeff. Nobody's gonna help you, Jeff. 6 or 0.2 divided by 5. Is that right? No, I'm not doing that right. Somebody help me.
Good. 0.446.
What is it? Point.
0.446.
446. Okay, so it's not as big as I thought it was. Yeah, why did I think it was going to be big? Wait a minute. Let me make sure. Bum, 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 bum. Square root 0.4 times 0.6 divided by 68. Yeah, okay. So did we find enough evidence?
No.
No, we only got barely, we didn't even make half a step up from the mean. Right? And we can round this to 0.45, so if I wanted you to, could you find the p-value? That's just gonna be, visually, it's just gonna be this area in the tail. So if I look up 0.45, I can do 1 minus the area I get. That would be the p-value. But even before we do the p-value, do we know the answer?
No.
Did we reject the null? Did we make it?
No.
No, we didn't make it, so we failed. We don't do this. We fail. We already know we failed to reject. So, just to address this, in case some of you guys are wondering why we even look up the p-value, since we already know the answer to the question, we know the answer to the question because we had an alpha. In real life, there's no alpha that's given. It's just a p-value, and then we have to come with our own alpha. So that's why we figure out the p-value. So does anybody see what the p-value is?
It's 1 minus z stars, so.
1 minus the area
Oh.
that you would get. So you have to look up 0.45 in the z-score chart.
The area of 0.45 is 0.6736, so 0.3264.
Okay. Which is huge. You expect p-values to be less than 0.05, whatever. That's when evidence is shown. That's stupid big. That's like, no, we failed this miserably. Which is actually good, because that's, we felt that, you know. I don't know, it's actually bad. I don't know. It's a horrible example, but first thing that came to mind. So the conclusion then is we fail. In fact, which one was the claim? The hoe was the claim, so I want to use this language right there. I want to talk about the claim. We have not found sufficient evidence. Suff, Evid, to reject the claim. I'm not even going to write it down because you just fill in that at most 40% of students in this class will remember, so you can just copy that, right? Because that's the claim. So there's one place in one course that you can plagiarize. Don't do it, kids. Ask ChatGPT. Yes?
How do we know how many tailors there are?
Hypothesis tests are developed to find evidence for this statement. What would show evidence that a percentage is greater? That way, and that's it. One tail test, because there's only one direction that would show, right? Not the band. So if it was not equal to, that's greater or less, that's two tail. If this is any directional symbol, that's one tail in that direction. Because again, if I found something down here, that's really not evidence, right? That's counter to what this says. Yeah.
I don't get how you get 2, 3, 2, 6.
2, 3, 2, 6.
Z-score.
Oh, here, this one. All right, look at your t-score chart. Yeah, totally. At the bottom of the t-score are z-scores. And the t-score chart is built for hypothesis tests because it's got one tail, two tail. Do you have a t-score chart? So if you look at one tail, 0.01, right? Okay. Oh. I don't know if I brought mine, shoot. Okay. So look at alpha 0.01 in one tail, right? So pick the one tail row, 0.01, go all the way to the bottom. Yep, and what's it say? what T-scores do, when I take a sample, I guess, and I guess watch some, how certain am I about the standard deviation I got? Well, I'm more certain if the sample is bigger. So if the sample is large, I feel really confident. So the smaller the sample, the more the T-score has to cover my ass for knowing something, not knowing something. That's why they see how they get bigger, bigger, bigger as my sample size gets smaller. But when my sample size is really large, I don't even need a T-score. I can just use the Z-score, because then I'm really pretty sure about my S being close to sigma. I don't know if that makes any sense.
That makes sense.
And then the good question is, what's large? And well, it depends on how precise you need to be. That's why it's left open.
Are there any handouts?
You got the practice final?
Yeah.
Did you? Did I give you? Wait a minute. You were here earlier, right? Because I gave you your test. Okay. By the way, I will be bringing some treats on the day of the final. And I will eat and you can watch. No, you can share in. Oh no, what in the world, man? I've never seen one do that. What did it? So when we do the final, you can just, let me just show you what I'm doing, but you can just come up and say, hey, Jeff, can you make sure? So hit second 0 to go to the catalog. You want to go to the D section of the catalog. Diagnostic 1. Now if you do the linear regression or that's so weird. It should stay on.
Oh, it turned off.
Yeah.
Did you maybe reset all those
It's really strange. But calculators like to remind us that they're in control. Yeah.
So the most recent test we got, the grade we got, was that after a curve?
No curve. Yeah, the average was a 75, which, doesn't make anybody feel better if they got lower than that, but that's a good average, yeah.
Can you go over one on the practice file? I'm sorry. I
No,
feel
you're
like I
fine.
should know how to do it, but
So I give you an average amount, I give you a standard deviation, and I say assume it's normal. So can you draw the picture? So bring out what they want from this year? Yeah? Okay. So you got it, Bella? So you got a normal curve. What goes right in the middle? Good. Which is
164,
standard deviation you don't have to put on there, but we understand that it tells me. And then the first question is the probability it's greater than 200. So where's that on the picture? Good. And I want to know the probability is greater than, so I want that area. I know it's normal, so I could use the z-score chart to find areas if I had a z-score.
So you do 200 minus mean over standard deviation?
Yes. Get a z-score, look it up, do 1 minus that because you want the area to the right. above, yeah.
What is this called?
Number 1 on the practice final. 1-1. What's the difference between 1-1A and 1-2A on the practice final? 1 subsection 1 subsection A versus 1 subsection 2 subsection blah 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 whatever. It's like reading a legal document.
Subsection 2A is, that's the X bar, so reason samples. So we're doing t-scores.
No,
That's.
We took a sample.
S and,
took a sample. We're talking about sample means. So what has to change?
the standard deviation.
Standard deviation.
So we do S over square root of
Well,
X.
sigma. That standard deviation came from all U.S. adults. It didn't come from a sample. Yeah. That's your problem. Huh? Okay. Say again. Let's see, chapter 3, 4, yeah, 5 is
Right,
uniform. 6, 7, 8, yeah, it's good. And then boxes tests, and then vice versa. Yeah. No idea. Yeah, it's just a bunch of numbers. I don't know. How's it going? It's routed to 2 places, right? Because it's only those 2 places. Yeah. So then if you look up 0.92, it's positive, right? It's 1, 2, and that'll be the area below, and we want the area above. 1 minus 3. Yeah. Go on.
Can you go over to
To which one?
2A?
2A?
Well, the 2 pieces of paper without.
Oh, 2 piece paper, blah, 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 okay. So probability of red, then green. So what's probably I reach in, I pick a red piece of paper. How many red pieces of paper? So number 3 is on a green piece of paper, number 4 is on a green piece of paper, number 8 is on a green piece of paper. So there's 3 pieces of green paper, right? So how many pieces of red paper? 3 out of how many total pieces of paper? 6. So the probably get a red first is 3 out of 6. Then I throw that away, or I eat it for some extra fiber. What's the probability to get a green then? 3 out of, no, I threw that first one away, right? Because it's without replacement. So I pick the first one, it's red, I throw it away. Now when I reach in, there's still 3 greens, but there's only, yeah. Okay. So if I would have said with replacement, then it would have been 3 out of 6 again, yeah. Okay.
So for 1 subsection 2A, so we do find the least standard deviation by doing sigma over square root of n, correct?
Yep.
So that gives us our 6.8059. So then we do 200 minus 164.71 over
The new
6.8.
standard deviation, yeah.
Right, and that gives us our new
Z-score. And then you look at it. So it's all the same work you did on 1A, all the same work we would do here, just using the new standard deviation instead. So you're still gonna make a z-score, you gotta look it up, do 1 minus, yeah.
Maybe a super minus that is.
Here's a funny question, when are test 3 corrections due?
The final.
Final, yeah. So anything you haven't turned in yet, you can just hold on to it if you want to and just turn it in on the day of the final. In terms of the best thing in the world that will both help you study and immediately improve your grade is any test corrections you haven't done yet. That'll help you study, and you've got a good chance to lift your grade because tests are the heaviest weighted things individually. Yeah.
Are we still able to turn test 2 corrections?
Yeah, you can turn in quiz 1 corrections. You just won't get anywhere near as many points as you could have, but
Notes.
yeah. So round it to 2 places. Like, because then you have to look up on here, and so it goes to 2 places. So that's just the z-score, it's not an error. So if you round that to 2 places, you get 0.92. So then you'll get 0.92. And that's the area that's below. So if you do 1 minus that, then you get the answer. Oh yeah, so I know it seems really picky, but the format of the conclusion composite interval is we are this and thus confident that our interval number to number contains the true thing. And it totally matters because our interval catches something that exists. If you turn it around, it sounds like we put an interval and then we see where's the mean gonna fall, which isn't true. The mean exists, it's something, or the real percentage or whatever it is. We have a certain chance that our interval catches that thing. Somebody else could come and make a different interval and they might not catch it, we might catch it, you know. It's not like I'm making an interval and then the real mean sort of falls somewhere. I know, it doesn't sound sweet. Yeah, the construction should be, we are blank % confident that our interval, blank units to blank units, contains the